Well, welcome back, guys, and as ever, I do hope you and your family are keeping well. So, now for your fourth lesson on gravitational fields, and what we're going to do today is look at Kepler's laws. Now, if there was ever a genius, he's your man, okay? Back in Germany, in this sort of period, he was using observational data of objects like the planets and the Earth that were going around the Sun, and he started to mathematically formalise how they orbited and what the shapes of the orbits were. And it's rumoured that Newton then came along and took Kepler's work and developed it into the gravitational stuff that he published in Principia. Okay, so a good way to kick off with Kepler is to look at the orbit of comets. And so you might know a bit about comets. They're those objects that come from a very long way, sort of beyond Neptune and what have you, and get pulled in by the gravitational attraction of a star, in the case of us, our Sun, and they go hurtling around the Sun and then clear off back into space. Okay, they might never come back. They might end up coming back again, and you see them later on, like Halley's Comet, or they might have an unfortunate collision with something on the way, like Schumacher-Levy 9, I believe, that crashed into Jupiter not so long ago. And I've seen comets, Hale-Bopp I saw, which was really, really impressive. You saw this massive streak of the comet's tail in the sky at night for day after day as it orbited the Sun. And the tail of the comet, that's another story, whether the tail is in front or behind the comet, whether it's actually got a tail behind it or whether it's rushing into its tail. But we'll leave that for maybe another lesson. So, an introduction to Kepler's laws. So I'm going to draw the orbit of a comet around the Sun, and I'm going to choose to do it on this bit of the page here. Now, bear with me, it's not an absolutely brilliant drawing. But it gives the general idea. I've got to try and get closest to the Sun over here. Okay, so I can improve that. It really should be a perfect ellipse. We should be really close to the Sun here, but you know, you get the idea in a quick video lesson. Okay, so let's have our little comet, and here it is. Okay. And the way I like to think about this as a human, because it's the way we think, is turn this diagram through 90 degrees, okay, and imagine the comet falling, okay? So you've got the gravitational pull of the Sun, so the comet is going to fall towards the Sun, okay? It's also got a velocity in this direction, so that force is going to turn the vector of velocity, okay? It's got a centripetal force on it due to the Sun. Okay, and remember the direction pulling in towards the centre of the Sun. Now, it's a very long way away from the Sun here, so it's going very slowly, and as it falls down towards the Sun, it'll go faster and faster and faster and faster, swing around the Sun, slow down, slow down, slow down, and kind of stop at the top, and then back again, and then stop again, and then back again. Okay, so if you think about it, if you just use F equals ma, okay, it will get faster here, but not only will it get faster, but the force is bigger, so the acceleration, how much faster it gets per second, will also get larger. So it's going at a very high speed here, close to the Sun. Okay, now if it's an icy blob of material, the Sun will, with the sort of energy coming off the Sun, will melt that material and blast it off the comet. And so if the comet's here, that's where you'll see the tail. Any which way. Okay, let's put the comet here, closer, stronger gravitational pull on it and going faster. And let's put the comet here now, and it's now whizzing around the Sun at a very, very high speed. But it's going to take time to go round, and we'll call that time, the orbital time, t, the time period to go around the Sun and get back to where it was. So you'll also notice that this is an ellipse. Oh yeah, okay, it's not a brilliant ellipse, but it's a sort of egg shape. It's not going round in a circle. And one of the things that Kepler formalised was the fact that this is true for all objects orbiting the Sun. So don't think about the Earth as going around the Sun in a perfect circle. Okay, it's very, very close, but it actually goes around in a slight ellipse shape. Okay, so what I want to do is use this kind of concept to describe what the three laws were that Kepler formalised, and then we'll do a little calculation. So now let's look at what those three laws were, and it's good to look them up and learn them. Okay, so Kepler's first law. So I'll just put Kepler 1. There it is. Okay. Well, what he said was that the orbits are always elliptical shape. Okay. So a planet's orbit is elliptical. Okay. That's the first thing, or it's an ellipse. But secondly, he pointed out that the Sun is at one of the focal points of the ellipse. Okay, so Kepler's first law, a planet's orbit is always elliptical, and the Sun will always be at one of the foci of the ellipse. Now, I'm not going to show you how you find or draw the foci, or you draw ellipses, but you can sort of imagine that there's a sort of point here and there's a point here that if you were to crush that together, those 2 points would come together and that would be a circle. Okay, so you've kind of taken a circle and stretched it. It's a little bit more fiddly than that. Okay, but you now know what his first law was. Okay. Now his second law is really, really clever. So I'll just wind that up a little bit. Okay. So Kepler 2. And I'll try and draw this correctly for you. Okay. I'll state the law first, and then I'll draw it on the diagram and try and explain it. So you need to take a line segment. So a line segment. Okay, joining the planet that's orbiting to the Sun, so joining the planet to the Sun. Okay, now in this case it's going to be a comet, and I'll draw a line segment between the two on here in a minute. Okay, if you take that line segment, okay, it always sweeps out the same amount of area for equal amounts of time. So sweeps out equal area for equal amounts of time. Okay. Now, if you can't visualize what that means, let me draw on the diagram, and I'm going to try my best to get this right. So, let me first do it with the Sun and the Earth in a bit of a sort of simple way. Okay, so if I put the Sun here and I put the Earth here, okay, and let's just kind of break with Kepler's first law and not draw it completely elliptically, but let's just draw it as a circle going around the Sun, because it still works. Okay, if you can imagine the Earth going around the Sun like that, okay, so let's prize this apart. A line segment joining the planet to the Sun. Okay, so here's our, let's do it in green, here's our line segment, okay, that one, okay, the spoke of the wheel, the radius, the R, okay, sweeps out an equal area for an equal amount of time. So let's wait a month. There we go. We've got this sort of chunk that's swept out. Let's wait another month, another month, another month. In other words, maybe, I don't know if I'm doing 12ths here, that might be the area swept out in 1 month, then the area swept out in the next month, and the next month, etc., etc. Now you might say, well, that's obvious because it's a circle, okay? But here's the clever bit. Let's take Kepler's second law and apply it to the comet. So if you think about the comet out here, or we could make it a planet if you like. Okay, here's our line segment. And the comet's going, should we have it going this way? Very, very slowly. So let's take an equal amount of time. Shall we say a year or so? So the comet might be there. Okay, it's got to there, and there's the area it's swept out. So that area is very narrow, but very long. Okay, now let's have the comet here. Well, let's draw our line segment. Okay, and it's whizzing along quite fast. So in the same amount of time, it might have got to there. And if you do the maths, because Kepler did, that area will be the same. Okay, let's imagine the comet's now sort of here, line segment, and it whizzes around the sun very rapidly. We're going to take the same amount of time, and there's the area it sweeps out. So if you compare that to the Earth model, okay, moving slowly, did we say for a year? So we've got that area. Moving fast, did we say for a year? Okay, this is a bit ridiculous, that close to the sun for a year, but there we go. Okay, still in the same amount of time, in equal amounts of time, sweeps out an equal area. So that's Kepler's second law. All we need to do now is have a quick look at the third law. Okay, and the third law is a little bit easier. Okay, so Kepler 1, 2, 3. So Kepler's third law basically states, so I won't write huge long sentences, that if you know the time period, okay, so remember what that is. The time period is the time to go round once, so 365-ish days for the Earth, and you know the distance from the object it's orbiting on average, and it's really important that it's on average, okay, r, so the average separation from the object, okay, you get a linear relationship if you square the time period and cube the distance, okay. So the square of the orbital time period of any planet orbiting the sun will be proportional to the average distance away from the sun cubed, okay? And that makes a very important point, that t squared over r cubed is a constant. So if you take any of the planets orbiting the sun and you know how long they take to go round, and you square it, and you divide by their average distance away from the sun cubed, you will get a constant number. Okay, so now shall we look at the velocity that a planet goes around the sun? And it's not a particularly easy calculation, so you might want to look over this a few times because it comes up quite a bit. So the first thing we'll do is we'll draw the sun here. So there's the sun, and we'll draw the orbit of the Earth around it. And we're going to assume, using my best drawing skills, we're going to assume that the orbit is circular, just to make, well, almost circular, to make the orbit calculation just a little bit easier. I mean, it's not far off. We know it's an ellipse, of course. Okay, so we've got a few things going on here. Firstly, it goes around, okay, once every 365 days or thereabouts, and that is the time period for the orbit. Okay, it's a time, a little t, yeah, it's a time in seconds or years, but because it's an important time, it's the year. In this case, it's important to us for the maths. We give it capital T and we call it the time period. Okay, we've got the direction that the Earth's going around the sun, and what you mustn't forget is that its vector of velocity is straight across there, then down, then that way. So it's going at a constant speed, but it's always changing its direction. So it's accelerating because it feels a force. So perhaps it's a good idea for me to draw a sort of tangential vector that way to show you that that would be the velocity at that point. It would have a magnitude and it has a direction. Okay. We know some other things. We know that the Earth is being pulled down towards the Sun with a gravitational force. And we know one other thing. We know from the centre of the Sun to here, we know the radius of the orbit. Okay, so the first thing is a little bit of sort of high-level GCSE, but it's a bit of A-level. What is this force? What is the maths of the force holding it in orbit? Okay, swinging something around your head. Do you remember the centripetal force? I find students often forget this when I teach it. So the centripetal force on an object, F, is equal to m, the mass of the object being pulled in, okay, so I guess it's a little m, times its velocity squared upon the distance it is from the object hauling it round, okay. So the centripetal force is mv squared upon r. Don't forget the v squared, please. Okay, but taking it further to A level, you also know Newton's law of gravitation, that this force here is a centripetal force and it has value mv squared upon r. So there's our v, there's our m, and there's our r. But it's also equal to minus, because the vector direction, g, m, that's the mass of the Sun, m, that's the mass of the Earth going round, over r squared. So what we can do is we can equate these two together. So we can say, well, they're the same. They give the same value. That if you know those numbers, you can work out the force that the Earth's pulled in by the Sun. Or if you know Newton's laws and you know those values, you can use that formula to get the same answer. So mv squared upon r is the same as minus gmm upon r squared. Okay, I'll put the minus in there for the sake of the vector nature, but it doesn't really matter because we've got an r here as well. Okay, so let's get rid of that to keep it simple. So let's have a look at what we can do. Well, look, we've got an m here and we've got an m there, and we've got to be a bit careful because those two m's are the same. They're the object being pulled round. So m and m go. Okay, we've got an r here and an r squared there, so that goes. Okay, so you'll notice that v squared is equal to g m upon r. So we've used two bits of physics that we knew to work out the orbital velocity of a planet around the Sun. But I want to take this just a little bit further and show you a way of working out the velocity value that we can substitute in here. So the brighter amongst you might have gone, well, okay, that's all very good, and we've got an equation here, but how do you know the velocity of a planet? How do you know what speed it goes round at? Okay, well, it's quite clever, and this is the next step of the sort of maths you'd be expected to do. So I'm going to go over here to do it. Okay, you'll notice that it goes around, and we're going to have a circular orbit. Okay, so all the way around, the circumference, the distance it goes round is 2 pi r, because the distance around a circle, the circumference, is 2 pi r. The next thing, oh yes, there is some GCSE and A level, that speed is distance divided by time. Okay. Well, what speed's it going at? Well, we know that in a year it goes around 2 pi r. So the speed will be the distance 2 pi r divided by, the time. Well, that was the year, wasn't it? Going around, so that's the time period. So the speed a planet will go round the sun really depends upon its time period, so sort of how fast or slowly it's going around and how far away it is from the sun. Okay, and now we can use that in this equation because we've got v squared is equal to gm upon r. So what we've got to do now is go v squared equals 4 pi squared r squared upon t squared. So if we take it over here, 4 pi squared r squared upon t squared, that's the v squared, is equal to gm upon r. So we've now got a way of working out the velocity. Right, it's usually at this point I hope people look at this and don't go, what's all that mean? You remember Kepler's second law, okay? That the time period squared is proportional to the radius cubed of any planet orbiting the sun. And can you sort of see there's a sort of t squared in here and there's an r squared and an r there? So what we're going to do is prize out of this one Kepler's second law. Okay, so a little bit more rearranging to do. So t squared, and you have to fiddle around with this one a little bit. Okay, will be 4 pi squared, and then we've got our r's to deal with. So this r would come over to there. So r cubed, all divided by gm. So just check that you can rearrange that. I mean, you might want to take t squared over here and gm underneath on this side and the r up there to make that r cubed. Okay, so the orbital time period squared of any planet going around the sun is proportional to the cube of the average distance it is away from the sun. So t squared is equal to 4 pi squared over gm r cubed. So you can see the relationship there, t squared is proportional to r cubed. Okay, and you'll notice that t squared therefore divided by r cubed is a constant, and that constant will be 4 pi squared over gm. Now, have a think about what this means. Pi is a known number, g is a constant, and the mass of the sun isn't going to change. So this is an incredibly useful law for working out things like distances away from the sun if you've spotted it in a telescope and know how long it takes to go round, or the other way round, that you can work out time periods if you know distances and vice versa. Okay, so kind of prizing out Kepler's second law from all the maths we've done earlier on. And I strongly recommend that you pause the video here, have a think about whether you understood the process I've gone through, because you could be asked to derive this in your A-level exam. So, yet again, you probably guessed that I want to look at this graphically. So, if we draw a quick graph prizing out this relationship. So, here are the axes. And let's make this one t squared and this one r cubed. Okay. You know that because that's a constant, we'll get a straight line. And again, I'm not going to try and draw the straight line at 45 degrees. There's the straight line. Okay. And t squared over r cubed being a constant will be the constant gradient. So here we've got t squared over r cubed. I won't write m, y equals mx plus c, because it gets a bit confusing what the m means. It means gradient in this case. And that will be equal to 4 pi squared big G over big M. Right, so let's put it all together now with a final calculation, and then we're done on Kepler's laws. So I thought we'd calculate how long does it take Saturn to orbit the Sun in its elliptical orbit. Okay, so we know the equation, t squared is equal to 4 pi squared upon gm, and I've taken the r cubed out, so I'm just going to put the r cubed there. Okay, now you need some data to work this out. So big G, you should have that on a formula sheet or know it, but I'll just write it down here. 6.67, really clearly marking the decimal point because in exams it can go missing. Times 10 to the minus 11. Okay, I'll leave the units off for the time being just to speed things up a bit. The mass, because it's in SI units, the mass of the Sun, that's the little symbol there for the mass of the Sun. It's a sort of subscript, a little circle with a dot in it. Okay, the mass of the Sun, huge value, 2 times 10 to the 30 kilograms, and the radius on average of the orbit between their two centres is 1.5 times 10 to the 9 kilometres. Okay, so what I'd like you to do is to work out the time period. In other words, the time it takes to go round the Sun, and can you please do it in seconds? So, how did you get on? I hope you didn't fall into the trap of kilometres here. It should have all come out nicely in seconds, and it's kind of a weird number, or nice number if you can say such a thing, 999 times 10 to the 6 seconds, so 999 megaseconds. And what I'd like you to do now, again, is just quickly pause the video, and can you put that number into years? Because it seems more sensible. How many years does it take for Saturn to go around the Sun? And remember that the planet is further away than the Earth, so if you get a number less than 1 year, think again, you know, something's gone very, very wrong. Okay, so pause the video and turn that number, please, into years. If I remember rightly, the A-level formula sheet, when you get it, actually has the conversion on it. But I'd like you to do it kind of manually, as it were, and work out how many seconds are in a year, and then work out how many years that is. So I do hope your calculation came out okay. And the time period for the orbit of Saturn around the Sun is approximately 32 years from our calculation. If you look it up in a textbook that does it properly and doesn't take into account all the assumptions that we've had, the sort of textbook value gives it as 29.5 years. So we haven't done at all badly there. Anyway, that's quite a long lesson and quite a complicated one on Kepler's 3 laws and the maths behind it. You've got to be able to do this, I'm afraid, if you want to do well in your A-level. So I suggest you go back and practice it and check the video again, and also have a really good look at your textbook and make sure that you could swap places with me if you had to, and with a bit of help and some notes, you could explain this stuff. Anyway, have a wonderful rest of the day, and I look forward to seeing you for another gravitational fields lesson very soon.